Okay. Last time we started 1.3. We're going to finish that up today. And we're going to start with graphing on the calculator this function. Okay, it's called the greatest integer function. Okay, anybody already know what that is? The greatest integer function. Okay, it's pretty simple. It's just defined to be the greatest integer less than or equal to a number that you're given. That's it. So it's defined to be the biggest integer you can have that's less than or equal to a number that you're given. And the symbol for it, in our book, they show it as like a double bracket around x on the graphing calculator. You can write it as the symbol int x, and I'll show you where that is on the calculator. Okay, so what have I said to you 4? What's the greatest integer that's less than or equal to 4? Yeah, Marina? 4. Yeah, 4 is the greatest integer that's less than or equal to 4. How about 3.6? What's the greatest integer that's less than or equal to 3.6? Sam? 3. Yeah. So that's basically the idea. We'll try with a negative. What's the greatest integer? Because now you got to kind of think a little bit. The greatest integer less than or equal to negative 2.9. Yeah?
Negative 2?
Negative 2. Yeah, negative 2 is the biggest integer. Remember, bigger means to the right on a number line. Biggest integer you can have that's still less than negative 2.9 is negative 2. Okay, so let's look at how we graph it. All right, so on your calculator, you want to go to y equals. Okay, and then under math. Okay, if you press math, and you go over to num, the one that says int, number 5, int. Okay, if you pick that, then just put an x and close the parenthesis. Anybody that had trouble finding it on a TI-82?
It's 4.
Yeah, it might be a different, but it's still roughly the same area? Yeah. Okay. Right, and hit graph. Now, that's what it's supposed to look like. Okay? If yours is connecting, it shouldn't look that way. Okay? The older calculators do make it look connected, though. Okay? But that's what it looks like. And what does it kind of look like? Yeah, it looks like steps. And that's another name for this kind of function. It's called a step function. Okay? So that's what it should look like. The reason we're using these opened and closed circles is basically to show whether it includes that point or it doesn't include that point on the very end of the step. Right? So when you're at 2, you include that. But then when you get to 3, right here, you have to jump up to the next step. So this step is only for every number up to 2.99999. And then when you get to 3, you jump up to the next step. Okay? Yeah?
So it's kind of like an inequality, the way that you would basically say, like you have your open circle over, let's say, negative 3. You're basically saying it's not including negative 3.
Right, it wouldn't be included. Yep. So for example, on the second step up, 2 is not part of the second step. Okay? Right there. I'm sorry. 2. Okay? For 2, you have to jump up to the third step. Okay? Up there. Because that's where the greatest integer less than or equal to 2 isn't 1. It's 2. Okay? It's also known as a step function. Anybody think of where that kind of function is used for something kind of real life? Think about maybe when you're paying for things. Is there any time that you pay the same amount for a range of things? It doesn't matter if it's between this amount and this amount, you pay the same price. But then if it goes above that amount, then there's a different price between two other values. When you're mailing a package, okay? You pay the same price for every package that's between 0 and 1 pound. Just make it simple, something like that. Between 0 and 1 pound, it's all the same price. Between 1 and 2, it's all the same price. Doesn't matter if it's 1.2 pounds or 1.9. It's still between 1 and 2. So that's an example where you might see that kind of function. Okay, any question on what a step function is or graphing a step function? Okay, so our next example was to find a complete graph. We've already done that. Then determine the domain and range. So remember, domain, those are your x values. Those are your inputs. Those are the numbers that you're allowed to plug into this function. What would my domain be for this step function? What numbers are you allowed to plug into the greatest integer function?
Infinity.
Okay, anything you want. Yeah, the domain is positive infinity to, yeah, includes all real values. So remember, when we write infinity, we use a parenthesis because we can't reach it. That's my domain. You can plug in anything you want. Okay, let's take a look at the range. So the range are the outputs. Those are the y values that you get. What kind of y values do we always get from the greatest integer function? This is not negative infinity to infinity. Yep, right?
Well, it's integers.
All integers, right. There are no decimals. You'll never get 2.7 out of the greatest integer function. Okay, it's all integers. So there's really, there's no notation using brackets and parentheses for it, so just write it out. All integers. Any question on the domain and range of the step function? Okay. All right, let's try it again. Just practicing the domain and range again. Okay, first we'll find a complete graph of 16x minus x cubed. And then determine domain and range. So we got 16 x minus x cubed. Okay, if you have one of the newer calculators, it'll show the exponent like that. If not, it'll show the caret symbol, and then you just put in the 3. Okay, generally start with zoom 6, which is your standard zoom, and see how that looks. Okay. I told you guys earlier that if you have an exponent of 3, that means the graph can turn twice. It is turning twice here, but the turns are off the screen. Okay, so this isn't a complete graph. We need to see more of the screen here. Yeah?
How do you get the x?
X, just press the button right up at the top that says xt theta.
Oh, okay.
Yeah. What do I need to adjust here to see more on the top and bottom? What two values, and which button would I press to do it? Oh, Michael?
Window button?
Yep, window. And which values do we need to adjust?
Y min and Y max?
Yeah, Y min and Y max. Let's try setting them maybe negative 25 to 25. Just barely. Okay, just barely a complete window. We got it in there. And I know because it's a cubic function, it's never going to turn again. It can only turn twice, and I can see both turns on the screen. So this side on the right goes down forever, on the left goes up forever. Okay? So for the complete graph, we just write down the window. X min, X max, Y min, Y max. Okay, now let's look at our domain and range. Okay, what's my domain there? What values am I allowed to plug into f of x? Oh, Brandon? Yeah, you can plug anything in. You can take any number, multiply it by 16, and you can take any number and cube it, and then you can subtract the 2. So there's no restriction here. You're never going to end up with dividing by 0. You're never going to end up with taking the square root of a negative. Those are generally the things you have to watch out for. Okay, so domain is all real numbers. And the range. Okay, the range is how far up and down this graph is going to go. Range is not what only you can see, but it's what actually is happening. So what's the range here? Oh, Brian? All right, so how would you say that? How would you write that down?
All integers.
It's more than all integers, because this also includes all fractions, all decimals, and all irrational numbers. So it includes everything. So it is infinite, but just how would you write that?
You'd have the parentheses. What's that?
How would you write it?
I don't know.
You want to help them out? Yeah.
You write the same as the domain.
Same as the domain, yeah. Okay, so the range is negative infinity, comma, infinity. Parentheses on both, no brackets. Yeah. Okay, this is a polynomial. Okay, we're going to learn eventually that polynomials always have a domain of negative infinity to infinity. All polynomials have that. The range, well, that depends. Think of a parabola. Parabola is a polynomial, but the range isn't negative infinity to infinity. Right? The range on a polynomial has to do whether the highest exponent is odd or even. Odd polynomials always have this as a range. Even polynomials generally either have a minimum and go up forever, or a maximum and go down forever. Right? They might do a couple more turns or something like that, but in general there's a minimum value and it goes up forever. All right, so let's take a look at a word problem. We're going to use the calculator to help us solve it. Okay, it says we've got a rectangular pool that has dimensions 30 by 50. There's a sidewalk around the pool of uniform width. We don't know the width, so just call it x. Okay, it says the area of the sidewalk is 600 square feet. They want to know the width. Okay, so we got a lot of words here, a lot of description. In this kind of problem, what do you think would be helpful to interpret or better visualize everything that they're saying here? Justin? What could we do for someone that's not good at reading all this? They'd be better at maybe
A diagram.
yeah, like drawing a picture, drawing out the rectangles, just to better visualize it. Okay, and I think once you have the image here, then you can see it a little better. So I'm going to start by drawing the pool, and then I'm going to put the sidewalk around it. So just draw two rectangles, one inside the other, basically. Okay, so here's our pool, or sidewalk, and then inside that, there's our pool. Okay, we know the dimensions of the pool are 30 by 50. Okay, there's a sidewalk of uniform width around the pool, and that's x. From there to there, and the same up at the top and bottom. Well, we're given some areas in this problem. Okay, we're given the area of the sidewalk. We could find the area of the pool. That's pretty straightforward. And somehow we need to use the areas to come up with a formula to find x. this is going to be an important number to use, the 600. Okay. How could you calculate the 600? You don't even have to tell me the numbers you would use, but just tell me what would be the calculation for the area of the sidewalk, maybe based on a couple other areas in this picture. Yeah?
Okay, so you know that your sidewalk is uniform, so you have to make sure that if you're calculating something, let's say you're calculating the area of the entire, like you're trying to calculate the area of the entire sidewalk, you have to make sure that you do 50 plus 2x. Like you have to make sure you add 2x because you can't forget that it's uniform on both sides.
Yeah, so this 50 plus 2x, that's the total length. Any total length of the pool plus the sidewalk. Any question on that? Okay, so let's see if we can come up with a formula here. So if we take the total area, let's calculate the total area first. Okay, so the total length is 50 plus 2x. Length times, and my width, Carly, what's going to be my width?
30 plus 2x?
Yep. Let's see, or sorry, I had it the other way around. So 30 plus 2x. That's right. So 50 plus 2x and 30 plus 2x. Yeah, let's FOIL that out. Okay, we're probably, if we're going to use the calculator to solve it, we might not need to FOIL it, but let's do it out. Okay, so Andrew, what's 50 times 30?
1,500.
Yep, 1,500. And we've got 50 times 2x, that's 100x. 2x times 30, that's 60x, so that's 160x. And then we have 2x times 2x, which, Silvio, is how much?
4x.
Close, not quite.
2x times 2x.
If it was 4x, we'd be able to combine it with this term in the middle, but it's not going to be a like term with that one.
4x squared.
4x squared. Generally, we like to write it in descending order, so why don't we just do it that way? Okay, now I have a formula for the total area. How can I use that to get the area of the sidewalk, though? This is the total area, but I still have a couple of the numbers we haven't used yet. Taylor?
Would you set it equal to 600?
Well, the 600 is not the total area, that's just the sidewalk area.
Add the area of the pool to the area of the sidewalk.
Yeah, we have to take into account that area of the sidewalk. So one way to do it is to either add it in or take the total area, subtract the area of the pool, and then all you're left with is the sidewalk. Okay, so that's my total area. Now what we're going to do is this. Total area, or actually we'll do it like this. Area of sidewalk. Area of sidewalk equals the total area minus pool area. Okay, area of sidewalk, we already know, that's 600. Now let's do this out. Total area minus pool area. Okay, there's my total area. What's the area of the pool? Yeah,
It's 1,500.
it's 1,500. So when we subtract that off, this last term just disappears. Okay, so all we get is 4x squared plus 160x. Okay, that's a quadratic equation. So algebraically, you have a few different ways you could try to solve it. I would divide out any common factors first if you're going to try to solve it with either factoring, completing the square, or the quadratic formula. Okay, what I'm going to focus on, though, is the graphing approach. Okay. So I'm assuming everybody can do this algebraically. Okay, and I might ask to see you do that on a test. Say, solve this with the quadratic formula. Okay, but let's do it graphically. If you have anything in there, just clear it out. And there's a couple ways you can solve it graphically. I'm going to type it in the way it is here. I'm going to type 600 into y1, and then I'm going to type the other side into y2. 4x squared plus 160x. Okay, and what am I looking for here? I've got two different graphs that are going to be drawn on the screen in a second, and I'm going to want to find what about the two graphs? I want to know where they're equal, but what does it mean when pictures are equal? What's that? Yeah, where they meet, where they intersect. Okay, so that's what we're going to look for. Now, keep in mind, we're on a standard window. Is that going to be a good window for this? No. I'm drawing a horizontal line up at 600. Okay, so my y values have to go pretty high. Okay, let's. The book gives us a suggestion of what to use as a window. Let's try 0 to 10 on the x. The reason I'm setting x min at 0 is because I don't care about negatives. Okay? I don't care about negative width for a sidewalk. This is a parabola. If you draw a parabola, a horizontal line, we'll hit it twice. The problem is one of those solutions is going to be in the negative part, and I don't care about it. All right? That one's wrong. So I'm only looking for the one solution that's on the positive side of the y-axis, on the positive part of the x-axis. All right, and let's set our y values. Let's just try maybe up to 800. Let's see how that works. Okay. Again, y min, I don't really need to see negative area either. So let's hit graph and see what we got. Yeah, that's good. Okay, if you wanted a complete graph, okay, not taking into account I don't want to see negatives, well, I'd have to go quite a bit further to the left. Okay? But you can tell a little bit that this red line is curved. That's part of the parabola. Okay, any questions on that? Does anybody remember how you find where they cross? You know, you can kind of trace and estimate it, but the calculator can give it to me exact. Anyone remember how to do that? Yeah, Orlando?
You want to hit second, then calc,
Yep.
and then go to intersect.
Intersect. Perfect. There's only two lines on the screen, so you can't get this one wrong. Pick a point on the first line. Pick a point on the second line. The guess just controls how fast it does it. And x is 3.45. Okay, this is perfect. If I don't want an exact answer, this is fine. If I said, tell me the exact width of the sidewalk, well, then you probably end up using your quadratic formula or completing the square. And the answer would have a square root in it. Okay? But we can't figure that out from this answer.
How do you get the intersection again?
Second calc, and it's the fifth option.
And then what do you press?
You just pick a point on the first curve, hit enter, second curve, hit enter, and then the guess, and hit enter. Okay, so it's about 3.45, what are we using, feet? Feet. Okay, so a little bit different approach to solving a quadratic equation that you may have never done before. That's how you do it. Okay, so the next thing they talk about in this section is projectile motion. Okay, so if you've taken physics, projectile motion is basically the movement of an object influenced by gravity, and the shape is a parabola. You can imagine like somebody throwing a baseball, you know, from like the outfield. They're throwing it in. The path that it makes is a parabola. Okay, and this is the formula that models that motion, where S of t is the height of the object as a function of the time. Okay, and it's negative 16t squared plus v sub 0t plus s sub 0. This negative 16 has to do with gravity. Right? If you've ever seen, has anyone used the number 9.8? If you've seen 9.8, then you're doing this in meters per second. Okay, we're measuring our speeds in feet per second. That's why we're using a different number. Does anybody know what v sub 0 and s sub 0 are? They're two important characteristics that control how high the object is going to go, how long it's in the air for, all that kind of stuff.
Velocity and speed?
Yeah, initial velocity and initial height, okay, above the ground. Okay. But you got to use units of feet per second if you're using this formula. And that's because of the negative 16. Okay, so our example says a model rocket is shot up, straight up from the ground with an initial velocity of 64 feet per second. So if it's shot up from ground level, what's the initial height if it's starting on the ground? Yeah, Nicholas?
0.
Yeah, 0. Okay, there is no initial height in this case. But there is an initial velocity, 64 feet per second. Okay, 2 questions. I want to know, what time will the rocket be 50 feet above the ground? And I'm also going to want to know, how high will the object go? Let's start with part A. When will the rocket be 50 feet above the ground? Okay. Again, I'm going to use a graphical approach. I'm not going to use algebra to solve this. So first thing we want to do is write out our formula, filling in what we've got. Okay, so our height as a function of time is negative 16t squared plus initial velocity times time. Initial velocity is 64 feet per second. And the initial height is 0, so we don't need that. Where does the 50 get plugged in? I should fill that in at the same time as well. About Shannon?
What did you say?
Where does the 50 get plugged in?
The 50 would be the one that you said.
Yeah, it's the s of t. If we want to fill that in, that's my height. It's very, very similar to the last one, just with different numbers. Put the left side in either y1 or y2. Put the right side in the other equation, and we're going to see where they cross. Keeping in mind, we don't want to see negative time, so we can set that to 0. And we don't need to see negative height, because this object's not going to go below ground. It's going to stop when it reaches 0 for its height. So let's put in 50. Okay, you have to use the letter x, even though the formula is a t on the calculator. You've got to use x for your variable. Okay. Now I know my y max has to be at least 50, but the object's probably going to go even higher than that. So maybe I'll try like 90. But I don't really know where to set my x values. So I'm going to just try to take a guess. Let's go 0 to 90. Or I'm sorry, 0. The x is how long the object's going to be in the air for. So I'm going to assume it's only in the air for 15 seconds. If I'm wrong, my graph is going to go off the screen, and I'll fix it. Okay, but my y max, I'm going to assume it doesn't go any higher than 90 feet. If it does, again, my graph will go off the screen, and I'll fix it. All right, so I was a little, kind of overestimated that a little bit. The object's only in the air for about maybe 5 seconds. Okay, so you don't need to set your x max that high if you don't want to. Okay, looking at that graph, okay, the blue line is where that's at y equals 50. How would you find the time when the object is above 50 feet? Yeah.
Wait, and
first, how would you describe the time when the object is above 50 feet? Is it an instant in time, like it just reaches 50 feet and then starts to come right back down? Or is it more of a range between two times that it's going to be above 50 feet? Yeah.
It's a range.
It's a range. It's between two times, and the two times are where these graphs intersect. Now you have to be a little bit careful with your intersect, especially the guess. Wherever you put the guess closer to, that's the one it's going to find. Okay, so I'm going to do the one on the right. If somebody else can calculate the intersect on the left, we'll get that time. So first curve, second curve, and now I'm going to put my guess closer to the intersection point on the right, and that's the one it gives me. So at 2.94, we'll say 2.94 seconds, this object is dropping back down below 50 feet. Okay, so at what time will the rocket be 50 feet above the ground? So between, and then we're going to need that first one and the second one. What was the first intersection point on the left? Yeah?
1.06.
Okay, so at 1.06, it's on its way up and it goes above 50 feet. And that's seconds as well. Okay, so between those two times is when your object is at least 50 feet above the ground. If I said to you, when is it exactly 50 feet above the ground? It's not between these two times, it's exactly at those two times. Okay, that'd be a slightly different question. Okay, part B, the maximum height. Okay, when you're finding maximum height of a curve, that can very easily get into calculus, involving a derivative of this function. We're not learning that this year though, so we're going to learn a different way to do it, which is on the graphing calculator. Okay, to find the maximum height, go second calc. There's a feature to do that, option 4. Now, notice my cursor is moving on the blue line. I'm on the wrong graph. I want the red graph in this case, so you just hit your up arrow, and then it'll switch to your other graph. Right? What you have to do is pick a point to the left of where you think your maximum is. Right? And then it puts in a line where it's going to start looking. And then pick a point to the right. So what you're doing is you're telling the calculator, I want you to find the maximum somewhere between those 2 points. And then the guess, the closer you are to the maximum, the faster you get the answer. And it says at 2.0000006, okay, 2 seconds. Okay, it's basically 2 seconds. It hits a height of 64 feet. Okay, so all kinds of questions I could ask you here. I just asked you what the maximum height is, but I could ask you when does it reach the maximum height? 2 seconds. Could ask you how long is this object in the air for? Well, you'd have to find where it hits a height of 0 again. And I think that's at about 5 seconds. Okay, so projectile motion, all kinds of questions. Yeah.
So what did you press again to get the 2 lines like the between?
Well, on this calculator, it'll put in the 2 lines. I don't think it will on the other ones. But it's second calculate maximum. Hit enter. Then go to the right of your maximum, hit enter. And then hit enter a 3rd time. Notice it changed its answer a little bit now. 2.000018. It said 06, I think, before. It's because the calculator is not really doing algebra to figure this out. It's just taking a really good guess. Again, it's at 2 seconds. We could prove that very easily with calculus. Okay. And the last thing for this section is what's called a piecewise defined function. Okay, a piecewise defined function is basically the idea is you're taking 2 separate functions and you're almost gluing them together, like a line and a parabola, and putting them together. So basically what you're saying is that if you give me an x value, just going to make up an example, less than 0, I'm going to use a certain function to find y. But if you give me an x value more than 0, I'm going to use a different function to find y. So you're using different functions depending on what the x value is. Okay, here's an example. We're going to graph this one. I'll show you how to do it on the calculator. But in this example, what I'm saying is I want you to use the function 3 minus x squared. I want you to use that to calculate y, but only if you're plugging in x is less than 1. So for any x less than 1, you plug it into the top formula. But if I give you an x that's greater than or equal to 1, I want you to use a different formula to find y. And the picture is going to be partially a parabola and partially a cubic function, kind of put together. Okay, and I'll show you how we type that in. Okay, to type it in, we've got to use parentheses. Okay, you have to put parentheses around your function. That's not normally something we have to do, but when we're typing in a piecewise function, we do. So type 3 minus x squared in parentheses. And then next to it, you're going to put another parenthesis. In this parenthesis is going to be the condition when you want to use that function. We want to use it when x is less than 1. Okay, well, we already know where x is. The less than symbol is under second test. Second test. And you have all your inequality symbols. We want, in mine, it's the 5th one down. And then type in 1 and close your parenthesis. So now what you've said is I want you to use this function when x is less than 1. And now type in the other one, x cubed minus 4x in parentheses. X cubed minus 4x. And if you have this calculator, make sure you don't accidentally put everything in the exponent like I did. Should look more like that. Okay, and that's when x is greater than or equal to 1. Now the calculator can't really draw open circles and closed circles, so you're not going to be able to see that part of it. So once you type that in, that's what you should have. Okay, and I'm going to do a standard window. I'm going to do zoom 6. Let's see what we got. Okay, what I want you to do is ignore the lines on the x-axis. Okay? Those shouldn't be there. So it's the blue one here. You're using that function for all values less than 1, okay? Parabola. Then when you hit 1, you're using this red function. Okay? That's what a piecewise defined function looks like. 2 different graphs put together.
Mine's not doing the standard window. It says it's an error.
All right, so we'll take a look at it. Okay, anybody else have trouble getting that picture? Yep, if you have the older calculator, it's going to try to connect them. These calculators don't like to draw things that are not connected. So, in fact, I can make it so mine is also connected. If I turn my asymptote detector off, does yours look kind of more like that? There's like a squiggle in between? Yeah. Okay, if that's what yours looks like, that's fine. That's just because that's what your calculator is doing. But it shouldn't look like that. Should look like that. Okay, any question on that? So this kind of function, we're going to learn some other names later on, but it's called discontinuous. Because if you were to try to draw this on paper, you have to pick up your pencil to draw it. It's not a connected function. Okay? The domain is all real numbers, negative infinity to infinity. If you give me any fraction, decimal, positive, negative, it's going to fit into one of these two. Think of any number in your head. It's either less than 1 or greater than or equal to 1. Any number. So domain is negative infinity to infinity. Range, well, we look at the range. It looks like it does go up and down forever, and it will. The blue part of the parabola goes down forever. The red part goes up forever, and there's even a little bit of overlap between the y values of like 3 and negative 3. So even though the domain and range are negative infinity to infinity, it's not a continuous function. Okay, but we'll learn more about that later on. All right, so 1.4, this is hopefully stuff you've done before. How you graph an inequality, whether you shade, dotted line, solid line, and it gets into slope and y equals mx plus b. Okay, so we'll go through this part really pretty quick. If you already know this, you don't need to write it down. But this is the slope-intercept form of a line. It's y equals mx plus b. M is your slope, b is your y-intercept. And when you graph this kind of line, this kind of function, it always makes a line. Okay, that's why we call it a linear function. Okay, it's a linear function. The slope and the y-intercept can be any real number that you want. Positives, negatives, fractions, or decimals. The only restriction, this should say not equals. The slope can't be 0, because then what happens is you don't have a linear function, you have a constant function. Y equals 2. Okay, if your slope is 0, you're wiping out your x value. That's a constant function. Okay, so m and b can be anything you want, except the slope cannot be 0. Okay, so here's a problem that can be modeled using a line. It says a house was purchased for an initial value of $60,000 10 years ago. Now, 10 years later, the house is worth $85,000. Assuming there's a linear relationship here, I want to find, first of all, a line that can model the situation, and I want to determine when the house was worth $71,250. What are the two things that you need to find the equation of a line? You need to know the, yep?
You need to know the slope and the y-intercept.
The slope and the y-intercept. Okay, so one thing we can do is, this 60,000 basically is one of those two things. It's the initial value of the house. So Orlando, what is the 60,000? Is that a slope or is that my y-intercept? Yeah, that's my y-intercept. I already know that. Now all we need to do is find the slope. Well, slope is rise over run, or change in y over change in x. Let's look at the change in y, okay, which is the change in the value of the house over 10 years. Okay, so change in y. The house went from 85,000, or I'm sorry, 60,000 to 85,000. What's the change in the value of the house there? Sylvia? So the house started at $60,000. It's now worth $85,000. How much is the increase? $25,000. Over how many years did that happen? 10. So 10 years ago, it was worth 60,000. 10 years later, it's worth 85,000. So my change in x is 10. Divide the 2, and that's your slope. That's the average value that the house increased per year. So my slope, 25,000 divided by 10, 2,500. So I've got M, I've got B. Now just write your equation. 2,500x plus 60,000. Okay, I'm going to skip over the second part of the question, which you could do on your own because we've already done it. When is the house worth 71,250? Fill in 71,250 for y. Plug that into y1. Plug 2,500x plus 60,000 into y2. You're going to end up with a horizontal line and a line like that. See where they cross. The x value of where they cross is how many years it took for the house to be worth 71,250. Okay, but it's the same thing we really did on the other two, finding an intersection. But this is new, writing the equation. Any question on that? Okay, so slope. You could have treated these as coordinates in the last problem and found the slope that way. It's basically what we did. But if you've got 2 points on a line, x1, y1, x2, y2, the slope is change in y over change in x. There's 2 lines that have special slopes, horizontal and vertical. Okay, with a horizontal line, all your y values are the same. So when you subtract values that are the same, you get a 0 in the numerator. 0 divided by anything is 0. With a vertical line, all your x values are the same. When you subtract 2 x values that are the same, you get 0. This time it's in the denominator. So when you have a vertical line, your slope is a number divided by 0. Number divided by 0 spells no. Okay, that's undefined. Okay, so two special cases of slope. Okay, so the next one, I want to find 2 equations. Special equations. I want to find a vertical line and a horizontal line that passes through the point 2, 3. What does the equation of a horizontal line look like? How does that start out? Oh, Josh?
The
Equation of a horizontal line.
Would it be y equals 0?
Well, that would be an equation of a horizontal line going through the origin. How about the equation of the horizontal line going through the point 2, 3?
Y equals 3.
Yeah, y equals 3. Okay, we can graph that on the calculator, and we've been graphing quite a few horizontal lines today. Y equals 3. How about a vertical line? Vertical line doesn't start out like that. It's a little different.
X equals 2.
Yeah. Vertical lines are always of the form x equals. So those are the equations of the 2 lines, the horizontal and the vertical, that would pass right through the point 2, 3. It's horizontal, y equals, then a number. A vertical line is x equals and a number. Vertical lines cannot be drawn on a graphing calculator. Not without trying to do something special. Because vertical lines are not functions. And that's generally what calculators in y equals mode like to draw, functions. We can kind of cheat and draw like circles as a top and a bottom half, but it's not really a circle. Okay, vertical lines are tough to even try to cheat and draw. Okay, how would you change 2x plus 3y equals 6 into slope-intercept form? What would be the first thing you'd have to do? Yeah, Josh?
Subtract 2x.
Sure. Subtract 2x from both sides. Okay.
Divide 3. And divide by 3.
Divide by 3 on both sides. divided by 3 is 2. Minus 2/3. One more thing we should probably do to make this.
With the 2/3 x or negative 2/3 x.
Yeah, we should switch the order since it's y equals mx plus or minus b, not the other way around. So negative 2/3 x plus 2. What's the advantage to doing that? There's an advantage to writing the equation this way versus the way I originally had it. Any thoughts about why you would do that? Yeah.
Well, now you can clearly tell what your y-intercept and what your slope is.
Right. If you know your y-intercept and your slope, you can graph that very easily by hand. You know your y-intercept, then from there you go down 2, you go right 3, there's another point, draw your line. It's very easy to graph. 2x plus 3y equals 6 isn't that hard to graph either, but now you can clearly see your slope and intercept. Okay. There's another form of the equation of a line. It's called point-slope form. That form is useful when they give you a point and a slope to start. It's y minus y1 equals m times x minus x1. So you still got to find your slope. It's just in this form you can avoid your y-intercept. You don't have to find it. Okay. So I could find the equation of the line with slope 1/2 passing through that point very easily using this equation. Just fill in my values. That's x1, that's y1. So it would be y minus 3 equals, m is 1/2. I got to be careful here. What's going to happen when I do x minus x1?
It'll turn into a positive 2?
Yeah, it's going to become x plus 2. And if this problem doesn't specify the form they want the equation in, that's fine. If they said they wanted in y equals mx plus b, well, now you could do your distributive property out. 1/2 x plus 1, and then add 3 to both sides. Okay, so you could just do out a little bit of algebra to change that to y equals mx plus b. Okay, and the third form of an equation of a line is the general form. We generally don't use this one a lot. We'd use something similar to it when we solve systems of equations. Line up all our x's, line up all our y's, but we usually put the constant on the other side. So when you solve systems of equations, when we get to that, we'll use something kind of like this. Okay, and next we'll take a quick look at parallel and perpendicular lines. Okay, so two lines are parallel as long as they have the same slope, but they have to have different y-intercepts. What if two lines had the same slope and the same y-intercept? They wouldn't be parallel. They'd be, yeah, they'd be the same line. Okay, perpendicular, a little bit trickier. Two lines are perpendicular if their slopes are opposite reciprocals. So two things have to happen. The slopes have to be opposites. So if one's positive, the other one's negative. And they have to be the reciprocal. So if one had a slope of 2/3, the reciprocal is 3/2. So an example would be 2/3 and negative 3/2. Those are slopes that are opposites and they're reciprocals. The only special case to that is a horizontal and a vertical line. Horizontal line has a slope of 0. A vertical line is undefined. But those are perpendicular, even though one of the slopes is undefined. Any questions on how you would do this? Write an equation of a line parallel to that and passing through a given point. First thing you'd have to do is what I showed you earlier. Rearrange this equation and find its slope. Once you know its slope, then you know the slope of the line you want to find because they're parallel. They're the same. So let me just find the slope, and then I think that'll I'll show you what to do from there, and I think you'll be okay. So if we solve this for y, we would have to subtract the 3x. I have a positive 1. And I'd have to divide everything by negative 2. So I get y equals 3/2 x minus 1/2. That's the slope of my new line because it's parallel to my old line. So my slope is 3/2. Now, you've got a couple ways you could do it. You could do y equals mx plus b, or use point slope form. x1, y1, m. Fill in those 3 values, and then that's your answer. And last thing we'll take a look at is linear inequalities. When you graph a linear inequality, this is the thing that you draw a line that's either solid or dotted, and then you end up shading on one side or the other. You use a solid line when you have either a less than or equal to or greater than or equal to. You use a dashed line when you have a less than or a greater than. After you draw in your line, then you've got to determine what side you're going to shade on. What I do is I pick a test point on one side of the line. If that point works, when I plug it back into the original inequality, then that's the side I shade. If that point doesn't work, then I shade the other side. And we'll try this example. Okay, so I'll give you guys a minute to copy that down and try that example, but solve this for y first. Try to graph the line. It should be either solid or dotted, and then see if you can figure out which side to shade. So first thing we did is we got y by itself, so we can see the slope and y-intercept. That lets us draw the line. In this case, it's dashed because we have a less than symbol. What's a good point to check here to see which side we could shade on? It would be very easy to do the arithmetic in. What's that?
0?
Yeah, the origin, 0, 0. So if we fill in 0, 0, we get 0 is less than 0 plus 4/3. Is that true? Is 0 less than 4/3? Yeah. So that means everything below the line we can shade in. Okay, so shade below. So everything on this side. Okay. If 0, 0 didn't work, then I would have just shaded on the other side. Okay, so that's how you graph an inequality. Okay, so for homework tonight, on page 31, 32 to 37, 45, 46, 50 to 52, and 55 to 57. This is mostly graphing calculator drawing functions. And then page 42 kind of skips around. 2, 7, 8, 11, 16, 17, 20, 24, and 27, 32, 44, and 77.